Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humor? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to Ask the Naked Scientist with me, Matt Jamison, and Chris Smith. Now, we're going to go to our first question, and it's one of those questions about something that's not really particularly pleasant, but I guess we should know about it. It's from Agnes, who says she was wondering about wax in our ears and how it gets there. Could you elaborate?
Yeah, the posh name for wax is cerumen, which is C-E-R-U-M-E-N. That's the stuff that accumulates. And it's a natural secretion, which the tissue which lines your external auditory canal, which is the bit you stick your finger in before your eardrum, it actually produces it. And the idea of earwax is that it's a secretion which can soak up debris, dust particles, dirt, pollen, bacteria, and it immobilises them, and then it slowly works its way out, falls out, and therefore carries the dirt out of your ear. It's your ear's self-cleaning mechanism. Because lots of people think that you need to clean your ears and get those cotton buds and things and jam them in. And in fact, it's a really bad thing to do. And if you ask an ear, nose and throat specialist, they will tell you that they cause more problems than they ever solve, those things, and that you should not do this. It's much better to let your ears clean themselves out. But there are some exceptional circumstances where they are useful if you get very, very clogged up ears. Interesting fact about earwax is there's actually two different kinds. There's dry earwax and stodgy wet earwax, and it depends on where you live around the world, according to which genes you've got in you, whether you have one type or the other. So people who live in Asia tend to have the drier form, and people who live in the West have a wetter form.
See, we've been on the air for 7 minutes, and I've already learned something. I'm going to throw away those cotton buds as soon as I get home, apart from the ones I use to clean between the keys on the keyboard on the computer. So are you saying that it will naturally just eventually just sort of fall out?
Yes, it should do. There's a sort of progression of cells where you make cells that line the auditory meatus and the auditory canal inside, and they work their way towards the outside, and so they carry debris out with them. So muck that gets accumulated inside should be carried out gently and just drop out naturally. And the wax gets softened by warm water, for example. So every time you have a bath or a shower, some water works its way and softens the wax up a bit, and it does help it to run out. You can help the process with a finger inserted and wiggled around. Doesn't taste too good. Here's a little tip for you about ears, though, Matt. If you get a peanut stuck in your ear, the official medical way to get this out is you get some chocolate, warm it up until it melts, and then you pour the chocolate into the ear, and then the peanut comes out a treat.
That's not as good as the joke I told you off air, I'll tell you that for nothing.
I've got an email here from Debbie, who says her father lives in New Zealand, in Flat Point, but she'll be listening to the answer to this question on this programme. So she's asked me if I could ask his question, which is, they're interested to know, when you have cars driving around on the road and their tyres wear out, where does all the rubber go? Now, it's an interesting question because I got asked this by someone in America a couple of years ago, so I was just looking up the answer I gave the guy in America, and the numbers gobsmack me, even now, reading them back again a couple of years later. The answer I came up with was literally billions of kilograms of rubber being deposited all over roads and in the air, all over America, because I did the sums for America, but we can extrapolate that to the UK, so let's have a look at the numbers. Well, there's about 300 million people who live in America. So if we assume that most families have a couple of cars and you divide the numbers out, you arrive at the stage of there must be about 600 million tyres in circulation in America. Now, if we assume that they're quite skinny tyres, so they're about 10 centimetres wide, they're a circumference of 3 metres. In other words, if you put a tape measure around the tread all the way around the outside of the tyre, it would be about 3 metres long. And assuming the tread that wears out is about a centimetre thick, if you times all those numbers together to get the volume of rubber on a new tyre, that's about 3 litres of rubber on a fresh tyre. And when that tyre wears out, let's assume it all goes. Now that means that you've lost 3 litres of rubber off of 600 million tyres, which, if you do the sums, works out to be about 2 million cubic metres of rubber, which are being shed on roads and into the air and things all over the country. And in terms of how do you convert that into mass, well, the mass is the density of something times the volume. So if we know the volume of rubber is about 2 million cubic metres, and we know the density of rubber, which is about 1,200 kilograms per metre cubed, if you times those two numbers together, that's 2 billion kilograms of rubber lost all over America per year. But it's not just rubber, and this is the thing about tyres. They're really bad for the environment because there's lots of heavy metals in the rubber too. And when the rubber gets rubbed off, the heavy metals get rubbed off on the road and into the environment, and that's not good. And so they're not just leaving rubber everywhere, they're leaving other kinds of contamination too. But it's certainly a big number. So there you go, Debbie. You can tell your dad in Flat Point that flat tyre might be bad news, but new tyres are even worse.
Is there nothing we can do with the rubber once it's sort of gone onto the road?
Well, not necessarily the rubber, but the really interesting thing is that lots of those rare metals, which are in very low amounts, and these heavy metals, which are in low amounts in the rubber, for various reasons. Some of them are just contaminants in the original oil. Some of them are added to give the rubber certain consistencies and behaviours. They are precious, and they're also very expensive, and they're very expensive to recover from nature. So if you've already got the metals on the road, it'd be quite nice to get hold of them. And there are research groups now in this country who, there's a group based in Wales for a start, who are doing studies on recovering a lot of these chemicals from the dust that you sweep up from the road. So you can go along the road verge, for example, sweep the dust off, and you can extract lots of these heavy metals from that in almost economically viable amounts. So that's what they're working on at the moment. So yes, you can get something out of that, but not necessarily the rubber.
Excellent. Got one from Joy here for you, Chris. My question is about expansion and contraction. When water reaches 4 degrees C, it stops contracting and expands. Other substances cool until they reach about 0, at which stage they disappear. I was wondering what would happen when water drops its temperature to absolute 0.
Well, we'd never know, because we cannot achieve absolute 0, because that's the temperature at which effectively all motion stops, and as soon as you get within a gnat's whisker of it, some energy comes in and puts the temperature up again. So we don't actually think it's possible to get to absolute 0, certainly not at the moment. In terms of water, very interesting, because the chemistry and the behaviour of water is what gives us the ability to have life on this planet, because as Joy correctly points out, when most things get colder, they shrink. And when they shrink, of course, you've got the same weight of something packed into a smaller volume, and therefore its density must go up. And when density goes up, of course, something sinks, because if you imagine you had water which is less dense than solid water, let's say, for the sake of argument, the ice would all sink beneath the water. And the result is that the planet would end up with a whole mass of ice on the bottom of the ocean, a little bit of water around the outside which would progressively freeze, and we'd end up as a solid frozen husk. And life wouldn't be possible, because we rely on the fact that ice floats and makes this nice white sheen on the North Pole and makes everything look pretty, but we rely on the fact that ice floats in order to make life viable. And so it's down to the fact that the water behaves in this strange way that we're here, for a start. But why exactly ice does this, it's all to do with how the water molecules line up. And there's very many configurations of water molecules, because water's a very sticky substance anyway, and the water, H2O, is itself a sticky molecule, because the oxygen is a bit negative and the hydrogen is a bit positive. And so adjacent water molecules, the negative bit of the oxygen snuggles up to the positive bit of the hydrogen, and they all stick together. And it forms these series of lattices, some arrangements of which are more stable than others. And as the temperature drops, the configuration of those lattices changes. And so the packing density, how closely the things can get together, also changes. And that's why ice has this very strange behaviour where it actually takes up more space, when it gets to a certain temperature, and then that's why it floats. In terms of absolute 0, I don't think I'd like to try and get water to absolute 0, because it would cost you an absolute bomb, and you'd never get there.
Got a question from John here, who asks why they are still using the chemical self-heating, in inverted commas, cans to heat coffee, and why can't they use it for other things?
That's an interesting thought. I've never owned one of those, but I would like to, and I think they're based on the same science as these hand or pocket warmers that you can get. Now, they work by a crystallization reaction, and it's reversible. So what you have is a chemical called sodium acetate, which is inside a sort of sealed container, and it's a supersaturated solution. So in other words, you make a solution warm, and you keep dissolving sodium acetate. This is the same flavour that you use in salt and vinegar crisps, actually. You keep dissolving that in the water until no more will dissolve, and then it's supersaturated. And then what you do is let it cool down, and you have some surface in there which is a bit rough or a bit sharp. And normally they have a sort of disc which is a bit like a sort of concave shape, which you can flick and pop in and out. And you activate the warmer by popping this disc. And what this does is create a sharp surface for what's called nucleation. And that is where, whenever you've got a sharp surface, crystals find it much easier to begin to form. It's like a key layer for them to begin to form. And once you've formed a number of small crystals, you can easily make some more. And the whole thing feeds back on itself and makes more and more crystals. Now, the way nature works, there's a concept called entropy, which is that the whole of the universe is trying to become more disorganised all the time. In other words, energy is trying to spread out, things are trying to mess themselves up, like my bedroom, and things are trying to get as far away from each other as possible. Now, if you want to turn something that's liquid, which is quite disorganised, into something that's a whole load of crystals, which is very organised, there has to be a payback so that there's an entropy increase, so the universe is happy. And the way that happens is by giving out huge amounts of heat, because then lots of molecules in the air get very excited and move around very fast, and this makes an entropy increase. So when this hand warmer gets activated, it's actually forming enormous amounts of heat by this crystallization reaction. And the same thing can be applied to heat up food. You can put this in contact with certain things like coffee, and when you activate them, this chemical reaction goes off, your food substance or coffee gets hot, and then you drink it. And this means that you can start with something very, very cold, and it's very compact, and it will heat up for you. Why you wouldn't want to do this with various foodstuffs is because there's a danger if you don't heat food properly that it could actually infect you with something. So I think there's a degree of sort of food safety element to this, and people want to make sure that when you heat things up properly that they are thoroughly heated and that there's not going to be a food risk there. But with something like coffee, which is sterile anyway, I should think it's probably very safe. That would be my best guess, John.
Thank you very much indeed. We have a question live on the phone from Alan. Good evening, Alan.
Good evening, Matt.
How are you?
Not too bad, thanks very much.
Excellent. You're through to Dr. Chris.
Okay, Dr. Chris. How are you today?
I'm very well, thank you, Alan. How are
good.
you?
Well, I can't go along with what you were saying about flaky ears and runny ears. You said it was...
Yes.
I always understood that it was a method of measuring the amount of fats and oils in the body. And if it was flaky, you wasn't getting enough. And if it was runny, then you're getting too much. And your finger was a dipstick.
I don't think you can use your earwax as an index of your cholesterol level, although I don't know of any research which has actually definitely compared it objectively, but it's an interesting thought. The earwax is produced by cells which line the ear canal, and as a result, if they don't have enough cholesterol, they'll just make more, because the body makes cholesterol in every single cell in your body. And that's why cutting out cholesterol from your diet is absolutely useless if you have high cholesterol levels, because your body will just make more. The thing that makes you have high cholesterol is actually the amount of saturated fat that you eat. So if you want to lower your cholesterol level, you need to cut the amount of fat that's in your diet. But the earwax composition is determined by the biochemistry of the cells in your ear canal, and the biochemistry of those cells is determined by the genes they have switched on. And if you have different genes in different populations, you'll have slightly different compositions of earwax. And that's why there is this Asian form of the gene, and there's a Western form of the gene, and they produce earwaxes of different consistencies.
All right. Can I answer the question I actually came on for now? I've recently bought an internet radio, and you've got thousands of stations around the world. And I was listening recently to Australian stations, and it occurred to me that to get from there to where I'm listening, it's going to make a journey. Does it have to go up and down from a satellite at any point? And what is the delay time from Australia?
With Australia, for instance, when I talk on the radio to people in Australia, which I do most weeks, that does go via satellite because they can get the fastest and the best connections that way. But there are also cables, and the internet, there's a big cable which goes from the north of Australia across Indonesia and then up across the Far East, Japan and China. And so I think most of the internet connectivity with Australia is actually subsea cabling. I don't think that's going via satellite because that will be very expensive. In terms of how the internet delays things, it's really interesting. You need very special protocols to talk reasonably on the internet, because the way the internet works, it was designed to make sure that the data arrives going from one place to the other, whether or not there's a problem. Because if you cut one of the cables somewhere, the data should still arrive, because the programming means that your data gets chopped up into lots of little pieces and then fired out via all these different routes until it eventually gets where it's supposed to go, and the computer at the other end reassembles it back together. Now that's fine if it's a computer program, because it can get the bits in a random order and put them back together fine, but when you're trying to have a conversation, it can be quite difficult, because if a bit of your conversation arrives faster than the bit that you said before, then the conversation can get all jumbled up. So you have to make sure all the bits arrive in the right order, and that means careful computer programming at each end, and that takes time and does introduce some delays. So internet radio is delayed compared with, say, terrestrial analog radio, which is probably the fastest way of getting signals across. We do something on a Sunday on The Naked Scientist, which is that we take the Naked Scientist radio program, which arrives in our office on DAB digital. We've got a digital radio in our office tuned to BBC Radio Cambridgeshire, and that then feeds the signal into a Mac mini computer sitting on the desk, That then digitises the signal. So it takes that signal coming down the wire and turns it into a stream on the internet, which then goes to another program on another computer in another part of the world, which then converts it into lots of streams, which goes into a program called Second Life, where people turn up and they have avatars and wander around as miniature figures on the internet and listen to the program. And the delay time between the signal leaving the studio in Cambridge and arriving in Second Life is up to 30 seconds. We think it's about 20 or 30 seconds average delay. So all that processing adds up to half a minute, would you believe, of time before you actually hear the end result out at the end of the day. So anything like that, your radio that you're listening to from Australia is likely to be really quite considerably delayed because of all the processing.
Yeah. Well, I think you've answered my next part of the question, and that's about the word streaming. It's a new word to me. What is streaming? Is this getting the signal in the right order?
Well, when people first invented the internet, the idea was that you would put bits of information. If you think of it in terms of, say, bags or packets of information, you could put all these packets in one place, and then your computer would say to another computer, "Give me packet A," and the distant computer would return to your computer packet A. Then your computer would say, "Okay, give me packet B," and you'd have to physically request each of these things, and then the packet would be sent, and then you'd say "thank you very much" each time. And then the idea of real-time streaming came along, where instead of you having to ask, "send me that, send me that, send me that," that the computer at the far end would generate a stream, almost like a river, of information flowing along that you can plug onto and just receive continuously as it comes along. And so you're getting a continuous stream of information, and that's good for things like radio programs and audio and music, because you're not having to continuously interrupt and get more information and then play it. You can get the whole thing as a continuous stream.
I see. All right, well, thank you very much. Very interesting.
Pleasure.
Is it true, Dr. Chris, that in sort of streaming and things like that, you're losing a little bit of the quality?
Yes, you are, because there's a system called compression. And what very clever people who write good computer programs have done is to come up with a way of making music sound almost the same, but take up only a fraction of the disk space on a computer. Because when you first make a bit of music, for instance, there are lots of different sounds which go into making the sound that you hear. Now, for a start, we can't hear, or most people can't hear, most sounds above about 15,000 hertz, 15,000 vibrations a second. And in fact, on the BBC, the desk that you're using right now, Matt, that is cutting off any frequency from your voice above about 15,000 hertz. So all that information is just being discarded, and you're only transmitting information of 15,000 hertz or below, which is what people's radios are receiving.
I thought it was something like that.
Well, that way, why send a whole load of data over the airwaves, which actually most people's ears can't hear? So if I was in the room with you, I would hear a slightly different... I'd be being hit by sound waves of slightly different frequencies than if I have you on a radio coming towards me, for example. Now, the other thing that you can do is that some of the data you can also compress a bit further, because you can write very clever computer programs that say that they recognise certain patterns of information, and instead of having to record every single one of the noughts and ones, they can say, instead of writing 01001, they could write A. And this means that you can have one letter to mean a data stream or series of 4 bits of information. And so you can compress the data. You just need to decode it again at the other end by putting the information back in. So it's a way of making sure you don't have to send as much information, which is good for the internet, because you don't want to have to download lots and lots of information when you could just say download a compressed version, which you then re-inflate almost at the other end. It's a bit like a bouncy castle. That it's a bouncy castle at your end. You deflate it, put it in a box, send it to me in the post, and then I re-inflate it in my garden.
Good stuff. Got a question here from John in Hunstanton, asking about static, and why is it that when in some offices, when you walk across the carpet and then touch someone, you get a little electric shock?
Oh, it's those terrifically big heels he's wearing on his trainers or something. It's where you've got really thick rubber soles. Static electricity is basically the accumulation of charge, either positive or negative, on an object which is electrically isolated. So if you take a balloon made of rubber and you rub it on your hair, the rubbing motion, the effort you're putting in, the work you're doing to rub the balloon on the hair can dislodge some charge from your hair, and it rubs onto the balloon, and you get an accumulation of negative electrons on the surface of the balloon. This means the balloon now has static charge, and that's why you can put the balloon against a wall and it will stick to the wall, because the negative charges on the balloon when you bring the balloon close to the wall, the negative charges on the balloon repel the negative charges on the wall, and they move away, leaving just positive charges which can't move. And so the positives and negatives attract each other, and the balloon sticks. You can do the same thing with a comb, run it through your hair, and then you can pick up little pieces of paper off of a table, for instance. Or if you turn a tap on and you have the drips coming down, you brush your hair with the comb and hold the comb close to the stream of water. You can bend the stream of water. It's because of an electric field. Now, when you walk across your office carpet, if you've got nice big thick soles on, that's just like having a balloon that you're rubbing on your hair, except in this case the hair is the carpet, and some charge can be dislodged from the carpet or from you, depending, and you end up charged. So when you reach someone else, their level of charge is different to your level of charge, and so there is a potential difference, a voltage between you. And when there's an electrical contact, i.e. you touch them, then there's an opportunity for the charges to equal out, because when there's an imbalance or a potential difference, then the charges want to flow from one place to the other to equal things out. And so you get a shock, which is the sensation of the charge flowing through a very small point of contact, and it's a very small spark which creates a high temperature locally, and it burns you a little bit, and that's why sparks hurt, because they're effectively burning you.
It does really hurt, though, doesn't it?
Oh, yeah, the biggest one I ever got. It wasn't actually me. I was in the room. I heard someone walk across a carpet, and I was little. I watched my dad walk across a room and touch a fridge. And he, of course, hadn't been trying to statically charge himself. And the noise was as though someone had slapped their hand into the door of this fridge and made a loud bang. I've never heard such a loud static shock in my life. But I'm told it was very painful at the time. It did elicit quite a volley of swear words. But one of the other places you'll see this is when you get out of the car. Because on hot days, when you've been driving along, you will find that the friction of air molecules bashing into your car is enough to make your car build up a charge, because the car is electrically isolated from the environment because it has rubber tyres. And so the car builds up a charge. When you get out of the car, because the car is a sealed metal box, it behaves like something called a Faraday cage. So you're fine inside it, but as soon as you get out of the car and you're touching the ground and then you touch the car, you're a convenient route to Earth for that charge that's built up. And you act as the piece of wire, and the current flows through you and it hurts.
A question following on from the Wi-Fi radio one we had a couple of minutes ago, Chris. Why did DAB transmissions arrive later than VHF? Comes in from George in Cambridge.
Yeah, it's a very commonly asked question, because what people are noticing is you buy a DAB digital radio and you put that on, and you still have your analogue radio on, say, in the other room, and you hear the pips telling you it's the hour in one room, and you come through into the other room, and then you're only just hearing them on the digital radio, perhaps half a second or a second later. And the reason is all down to processing, because when a signal is transmitted, the first thing that happens is that you talk into a microphone, and the microphone converts sound waves, which are effectively pressure waves coming through the air, into electrical signals. So you get an electrical version of the sound wave in the wire. That goes along the wire and into a desk, and the desk then effectively turns it into a radio wave, and it goes as an electromagnetic wave through the air and until it hits your aerial, and the aerial gets hit by this electromagnetic wave, which induces an electrical current in the aerial, comes down the aerial into your radio, and the radio then converts the electrical signal back into a sound wave again. That's the simplest form of radio, and that's how analogue radio works. Digital radio is very different. What digital radio does is it's a bit like if you go to the seaside or go to a river and you see one of those height meters that tells you the height of the water. And if you watch waves coming through, you can see that some waves are high, some are low. And what digital is doing is taking the sound waves, a bit like the sea waves, reading the height of the wave about 48,000 times a second and noting it down. Okay, at this point in time the wave is this big, at this point in time the wave is this big. So you effectively have got a table telling you the shape of all of the waves coming in. It then turns that table of the wave characteristics into a sequence of noughts and ones. That's the digital signal, and it transmits the noughts and ones rather than the wave. And when it gets to the other end, you have a decoder which reads the noughts and ones and then turns them back into the wave, and then turns the wave into sound waves that you can hear. And it's those extra processing steps, making the series of noughts and ones and then decoding the series of noughts and ones at the other end, that takes the time, because you have to feed it through lots of complicated electronics to do that for you. And that just doesn't happen instantaneously. It does take time. It introduces delay, and that's why you notice a disparity in the time. So if you're setting your clock by the pips and they're coming out of a digital radio, it's actually wrong.
We've got someone called Foxy who called us in. They're doing experiments with seeds in space. What would happen to cucumbers, for example, in zero gravity?
Oh, I don't know what happened exactly to cucumbers, but the whole point about plants growing in space is really big business for a number of reasons. Chiefly that it's becoming apparent that at some point we're going to want to explore further into space, and that means taking food with us or growing food on the move. And the problem with growing food on the move is that you rely on plants to do that for you, because they have the secret to how you capture energy from the sun and turn it into chemical energy that we can eat. Now, for the last few years, scientists have been looking at how plants respond to microgravity or zero-gravity environments. And in fact, there was an experiment on the Columbia shuttle, which unfortunately blew up in 2003 when it was coming home. But one of the experiments on Columbia did actually survive, and researchers managed to track down this remnant of the experiment, and they found it on the ground. It fell to Earth as a piece of debris, but because it was well packaged, they managed to actually rescue it. And the experiment had been to send some moss into space and to grow the moss in the space station and then recover it after a successful orbit and see how it was growing, to see if it would grow the same way as it does on Earth. And it showed really bizarre growth patterns. What it did was to grow in a spiral pattern, just like you would draw if you took a pen and just did circles that got progressively bigger and bigger and bigger on a piece of paper. Why did it do that? Well, it turns out that plants have a very clever mechanism for telling what's up and what's down. That's how when you plant a seed in the soil, it knows which way to grow up towards the light and how to send its roots downwards, because inside a plant's cells there's something called the cytoskeleton, and this is a network of fibres which crisscross the cell and they hold the cells together, but they also are sensitive to stretch. And inside the cells are little grains of starch, and when these starch grains fall under gravity to one side of the cell, they deform or push on this cytoskeleton, and that tells the cell that must be down. It's like a cellular spirit level, if you like. And if you turn that system off, the cells don't get this up and down reference signal anymore, and so they default to their default type of growth, which is to go in a circle. And so this is going to be a big problem when we want to go on long space journeys, how we're going to get plants to think they're back in gravity again and grow in a straight line. But that's why they're very interested in looking if all plants work like this, or if there are some that have other mechanisms for detecting which way they want to grow. And so that's why these experiments are very important.
Excellent. And we've got a question we need to answer in 2.5 minutes from Kevin, who says, if we replace our body cells every 7 years, how can we have any memory?
OK, well, that's not entirely true where the brain is concerned, because in some parts of the body it's absolutely right that we do replace our cells and they're continuously being turned over. And depending upon how likely the tissue is to be damaged or destroyed, you grow more cells more quickly than others. So if you look at, say, the lining of your mouth and your gastrointestinal tract, your stomach, for example, the cells there are being replaced at a furious rate. Thousands of cells every single minute are being made there, because as food goes through you, it goes through a bit like a Brillo pad and it scrapes off lots and lots of cells, and you need to replace them. Similarly with your skin, you're continuously touching things and rubbing off cells. The body loses about 40,000 dead cells from your skin surface every single second. So that's enormous amounts of skin, which over a lifetime weighs about 1.5 stone. So you have to replace all those things. But some tissues don't have that rapid cell turnover. They have cells which are made once and they have to last a lifetime. And the nervous system is very much like that. Lots of cells in the brain. You make them when you're developing inside your mother and for the first year or two after you're born, and then you stop making any new ones, and you have to rely on a lot of those cells to get you through your life. And that's why brains clap out as we get old and get things like Alzheimer's disease, because it's very hard to make new nerve cells to replace the functions of those that are being lost. So memory is encoded by connections between nerve cells, and those nerve cells don't change, and that's why you have memories. If you lose those cells, you can lose your memory, and that's what happens to some people who unfortunately do get certain brain diseases.
That's it for today. Thanks for listening, and join Sue again next week.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.